All right, so this video is going to be short but sweet, right? So we're going to be talking about carbon 13 NMR, and carbon 13 NMR, fortunately, is pretty much the same as proton NMR, except we aren't looking at the proton nucleus anymore. We're looking at the carbon 13 nucleus. Remember, we did state in a previous video that carbon 12 is NMR inactive. And so that's why we are observing the carbon 13 NMR. And unfortunately, carbon 13's natural abundance is only 1.1%. And so what that means is that we will have to make basically a very concentrated sample in order to observe a carbon NMR of an organic substance, and they take way longer than proton NMR. Okay, so just way longer, unfortunately. And it's just the nature of the lack of natural abundance. So since it's only 1%, that's why we have to do essentially. If you think about it, like 100 times, it takes 100 times longer, right? In theory, the proton NMR is literally of protons or hydrogens, which is almost all of the natural abundance of the hydrogen isotopes, all of which there's three of them: hydrogen, deuterium, and tritium. And the regular hydrogen atom is that by far the most abundant. And so that's why it's so easy to gather an NMR. You can literally grab it in seconds, whereas sometimes a carbon NMR can take days or even like longer than that. And so just to give you an idea, in terms of practical applications, they're not the best. However, they are extremely instructive. And like I said before, luckily they are very similar to proton NMRs in the way they function. So we still use the radio waves, the magnets, and we have the magnetic fields of the carbon atoms being oriented with or against, or reinforcing or opposing the applied magnetic field, and that can result in a variety of chemical shifts for those carbon atoms. And one thing that's very different, though, is that the low natural abundance of the carbon 13 isotope reduces the chances of coupling, because we really need a carbon 13 next to a carbon 13 in order for coupling to occur, and that's not as likely as it is having two protons next to each other, which are almost 100% natural abundance, right? So that means we usually just see singlets in our carbon NMR, which is still helpful because we do have this chart, which is very similar to the proton NMR chart, where we have just a typical alkane, and that ranges from 5 to 45. Now, that brings me to an important point, is that the carbon NMR can range from 0 to maybe 250 ppm is like a typical window that you might see, whereas the proton NMR, so let me write this, carbon 13 NMR, 0 to 250 ppm, and then the proton NMR was 0 to, I said 12 or 14 ppm. Okay, so that window is drastically different, and remember, that's just based off of the frequency of the electromagnetic radiation that it absorbs, and that's an inherent property based off of the magnetic environment of those carbons. But the cool thing about this spectrum is that they look pretty much identical to proton NMRs, other than the coupling, and so we'll see that in a second. But the range is different, right? So 5 to 45, we do have a Z atom where it's NOx, so an electronegative atom that ranges from 30 to 80. If we have an alkyne, 65 to 100. The alkene was 100 to 140. The benzene ring, or the aromatic, 120 to 150. And then the carbonyl, which is 160 to 210. So notice the relative shifts, chemical shifts, are pretty much the same. So this is going to be the upfield stuff, and that's like hydrocarbons or maybe with a little electronegative atom on it. And then we get kind of the alkynes in the middle, and then the alkenes and aromatics are further downfield, and then the carbonyl carbon has, at least this in this case, is the furthest downfield, and that was kind of the same for the protons on a carbonyl carbon. So like aldehyde and carboxylic acids, those were extremely downfield, and so they do parallel one another, and we can see that in this particular structure compared to this one. So these are, sorry, I'm trying to have them side by side almost, or not side by side, but stacked on top of one another. So this is a proton NMR, and this is a carbon 13 NMR. Actually, before I do that, let me, you might have seen it already, but that's all good, that's all good. Let's draw this structure out. When we're looking at proton NMRs, here, let me draw this in like a different basic color. So when we are drawing, let's say this is 2-butanol, so 2-butanol, and a typical question when we're discussing proton NMR is how many unique resonances or how many signals, how many protons are in here, and we know how to do that, right? So this was a common example that is a stereogenic center, and so we have one proton there, we've got another proton there that's unique, we have these hydrogens here, which are all unique. We've got our other blue hydrogens, which are unique, and then we've got, what color? We'll use purple. This is a hydrogen that's unique to the other hydrogen that is a part of that CH2. I'll do poopy brown. Boom. And therefore we would have 1, 2, 3, 4, 5, 6 signals for 2-butanol, this particular enantiomer. And remember, that's because these guys are diastereotopic. Okay, and so the same process is being applied to determining the number of unique resonances for carbon 13. So ultimately what we were looking for when deciding unique proton resonances is planes of symmetry, right? So if we have that OH there, I'm not going to draw the hydrogen as the wedge anymore because we don't really care about the hydrogens anymore. But what we want to do is look at the carbons and see if they are similar to any other ones or unique. And in the same manner, if we did have a carbon that was bound to just one proton, and it's the only one of its kind, then that's going to be a unique resonance. Okay, we have a carbon here that's the only CH2 in this molecule, and then we do have this guy right here and this guy right here, which are CH3s, but just as the protons were unique, the carbons are going to be unique as well. They are not the same. They're not chemically or magnetically equivalent. The red carbon is closer to the OH group than the electronegative atom in there, and so it's definitely going to have different electronic environment. And so in this case, what we've determined is that there are 4 unique carbons, right, for this particular structure. And it's pretty straightforward, and we do it in the same manner as we did with protons. And so hopefully we've practiced that skill and we are good to go on that. And so that brings me back to this. These 4 unique resonances show up here, 1, 2, 3, 4. And so does how many did we decide? So we had 1, 2, 3, 4, 5, 6 different resonances in the proton NMR. This is a little bit harder to tell because the resolution, but let's just take a look on what's obvious. So we have 1, 2, 3, 4. There's 1 down here, 5, and then it looks like there might be something else going on either here or here. Now, of course, that's not up for you to kind of decide in an exam type format. If it won't be ambiguous, but that's actually not even the point I wanted to make with these structures. What the point that I wanted to make with these structures is that was just extra fun, because we like to have fun. All right, so the point that I wanted to make is that the proton NMR and the carbon NMR, they mirror one another, right? So I would say actually that the carbon 13 mirrors the proton NMR. Okay, and so we have, let's see if we can move this over a little bit so that it's more obvious. Yeah, so you can kind of see that this peak right here is more or less the same relative area as these three. And then we have one that's further downfield that corresponds to that one. And so that's pretty much the cool thing. That's the cool thing about carbon NMR, is that it kind of goes hand in hand with proton NMR, and you can use them together to determine the structure. For me personally, I like to use proton as a means to discover or determine the chemical structure of something, but then carbon NMR can be used to kind of support the idea of a given structure or something like that. So really useful. And one last thing I wanted to mention is the fact that we can actually use mass spec. Now we can, at least, because we know about all of the NMRs and the mass spec and IR. We can use all of these tools together to figure out the structure in the end. So let's say we didn't get that structure to butanol initially. What we could look at is, okay, well, we have the mass spec. So the mass spec, this tells me I have 74 for my M+. It's not as obvious in this one, but it might be given as well. Okay, and this is really important because it's going to give us a general structure or chemical formula for our organic substance, our unknown, quote unquote unknown. And then we can take a look at the IR, and if this wasn't here, we would look at the structure or at the NMR spectrum and see, okay, well, that is typical of an OH stretch, and so we probably have an alcohol. Then we can go back to the mass spec once we've kind of determined that we have C4. Remember, using the rule of 13. Well, let's just do it, actually. Let's go for it. We've got 74. Oops, that's the erase. 74 divided by 13. So that's 3, 4. Let's see. I think that's 5. So 5 times 13 is 65. So that means we have as C5, H5 with a remainder of 9. And so we add the 9 to this hydrogen count, and that gives me C5, H14. But we did determine from the IR spectrum that we do have an oxygen. And so what we can do is subtract 16 in the form of a carbon and 4 protons, and that gives us C4H10 and then oxygen. Okay, so 3, 6, 7, 8, 9, 10 for oxygen. And if we did the math, we would determine that there are no degrees of unsaturation. Okay, and so that means we don't have any double bonds or rings. Okay, now what we would do after this is kind of predict some structures, right? So you could say, like, okay, we have 1, 2, 3, 4, And then there are essentially two places that a an oxygen or an OH can go on here. So there's one here, or there's one here, right? And so if you put that OH there, it's the same as here. So that because there is symmetry to this molecule, and so that's why I'm saying there's only two options in this case. And then let's see, what is another option? I guess technically you could have something like this where the OH is here, or it could be here as well. So maybe this, I don't want this to be confusing, so let me just erase that. Let's draw the blue structure where we have boom, boom. Okay, so now these would all technically satisfy the mass of 74 as well as the OH peak here. And so what we can do is use the proton NMR and carbon NMR to determine the number of unique resonances. If we were going to say this one as an option, you can see that there's only two unique resonances because this guy and this guy are all the same. And so this only has two unique hydrogens. This one right here on the top is 1, 2, 3, 4, 5, 6 resonances, so that's 6 H's. This one has 1, 2, 3, 4, 5. 5 H's. This one has 1, 2, 3, 4. This one right here is the same, so that's 4 H's. And so that's what we would want to compare that to this proton NMR. And we said it's obvious that there's 1, 2, 3, 4, 5 at least, if not more. And so that would immediately eliminate this one and this one. We'd have to look a little bit more closely to kind of notice that if there's 5 or 6, because remember, diasteric protons, although they are technically different, they might show up very close to one another to the point where we can't differentiate. So we'd actually have to have a good image of that proton NMR and then zoom in very closely to see if we can see some small coupling for those geminal protons. And so all right, so the other thing that we can do is, I'm going to use pretty in pink because I like that. We did say that for this particular structure right here, we had 1, 2, 3, 4 carbons, okay? And then for this one, we have 1, 2, 3, 4 carbons as well. So that's not super helpful. But here's the cool thing about incorporating all of the spectroscopy elements is if you look at this particular peak right here, what color do we want to use? Let's use like a cool, nice color right here. I don't know what this is, turquoise. We got this one right here. That is about 59, right? And so if you do 74 minus 59, you get 15. And what do we know about alcohols in a mass spec? Well, they undergo alpha cleavage. Boom. All right, so which one of these will undergo an alpha cleavage and give you a mass of 59? And drum roll, please. What we've got here is not failure, but success. Boom. Cleave that. Remember that CH3 radical, that's got a mass of 15. And so subtracting that from our leftover molecule gives us that mass of 59, and therefore we've got our structure using all the points of or all of the tools that we have for a spectroscopy. So super fun stuff. Definitely takes some practice, but carbon NMR and proton NMR are very, very similar, and so I like to personally view them like this, where they're kind of stacked, and then that, or if you only have one of them, for example, like the carbon, I think we've practiced maybe proton quite a bit to the point where you can kind of get the general idea where chemical shifts are going to be and what they correspond to, like what functional groups. But carbon NMR might be a little bit more difficult, but if you envision this scale being 1 and then this is kind of zoomed in, so it throws it off a little bit, as you saw with the lining up of those resonances. But let's say you just called that 12 here and 0 here, and then you just don't even look at the scale, you know that this is where the hydrocarbon protons show up. This is where we start having those heteroatoms, like the electronegative atoms, bound to those carbons, or which have protons on them, or even the proton directly, like alcohols. And then we also have, over here, this is where we would start to see the aromatic resonances, and then our aldehydes and carboxylic acids. And so you can kind of just visually estimate where those things are going to show up. And this is really helpful to do, and I would strongly suggest you do that. Okay, so with that is all for NMR. So check out the practice videos on for the problems, and let me know if you have any questions.